And there's more things in the race.
Here's a nuclear reaction. Here it's written like a chemical reaction. Okay. This is the bombarding particle. This is probably an alpha particle, right? Yeah? Okay. Bombarding, ordinary nitrogen, right? Okay. And what's released is a proton. Okay. And notice several things. If we add up those numbers, 4 and 14, we get 18. If we add 17 and 1, we get 18. It's simpler than chemical reactions to balance, right? Because we don't really care about the electrons. Okay, so these numbers are always going to add up. We're not going to destroy an entire nucleon number. In fact, we can't. Hadrons, those are hadrons and they're conserved. So we can't destroy those. And then notice that the charge here, this is charge on the bottom, it's proton number, right? Proton number is conserved here, so this and this, this and this, right?
That way it holds a large hadron collider.
Because they're large. No, it's just a large collider of hadrons. Hadrons are just the missiles that they're using because you start off with. Okay. Now, you can write this particular reaction, okay, this way. Apparently, okay. Apparently, this is the way that and when I took nuclear physics, okay, this is the way that we learned to write these things. And so what it is in the parentheses here, you've got, this is the bombarding particle. This is the emitted particle. Right? Okay. This is the original nucleus. Right? And then this is the final nucleus. Yeah? Original nucleus, final nucleus, right? The nucleus of origin, right? This is our final nucleus. And the reason that they do that is to make these problems harder for you.
Well, I was going to say, like...
No, I don't know. I guess it's shorthand or something like that, right?
So that's not actually the equation, it's just the way that...
It's just a way of note of these two things say the same thing, right? So what you need to know is there's these particles that we use, and there's a shorthand for them, right? And all you need is the recipes, and I'll give you the recipes on like the little skill sets and I believe the test, right? Okay. So an alpha particle, if they say alpha, use a 4,2 helium. Look up the mass of helium, use that for the reaction, right? If they call it a P, right? A lowercase p, well, just use hydrogen. Okay, that's a 1,1 hydrogen type thing. I'm being confused by this. Okay, and then if it's a D, okay, if it's a D, that's deuterium. That's a 2,1. That's an isotope of hydrogen with an extra neutron. Okay, and then if they use T, lowercase t is tritium. By the way, water with deuterium as the hydrogen, okay, is heavy water, if you've wondered what that is, right? And then tritium is a radioactive isotope of hydrogen. Yeah. I think it's got a half-life. There we go. Yeah. So write these down. I think you've got them. Do you have those in there?
Yeah.
Yeah, you do. In fact, I even put the masses in there. Okay. And then a neutron. A neutron, remember the recipe for a neutron is 1 nucleon but 0 protons, right? Okay. And then a gamma, of course, a gamma is 0, 0. Right? It's 0. It's just a photon, right? Okay. It's just a photon. Doesn't have charge, Doesn't change the charge, doesn't change the mass number, just changes the excitation level from 2. That's right. Okay. And then, of course, we can look at the mass of these reactions, the left side mass versus the right side mass. What if this side here is less massive? What does that mean? Energy was released, because the question is, where'd the mass go? Well, it turned into energy, right? Because mass is conserved, so if it goes away, right, then you had to release energy, right? So if this has less mass, if mass decreases, less mass means that it's exoergic, which means it gives off energy. Yeah, an erg is actually a unit of measure of energy that we didn't do, right? And if this has more mass, if this side has more mass, doesn't mean it can't happen. It means requires energy. Where would the energy come from? The bombarding particle would have to be given that much energy. How do we do that? That's what particle accelerators are for, right? That's one of the things we use particle accelerators for, is to give the bombarding particle enough energy to make a reaction. So if it's got more mass, then it's endoergic, right? Or, you know, and then when we did chemistry, these were thermal, right? Exothermic, endothermic. I don't know why they say ergic. Sounds better. That doesn't sound like you should be paid more if you say ergic. It's an exoergic reaction. Whereas endothermal is sort of more, I don't know. I really don't know. So exo, just remember exhale. It's giving off energy. Endo, I don't know. Don't know. Yeah? Are you guys ready for the excitement here? An example. So for these ones, the question is, what's the initial nucleus, right? And it's written this way. It's written this way, question mark. This is how it'll be written, right? So the question is, what is this guy here? Well, I'm just going to write the numbers out. So a neutron is a 1, 0. That is, it's one nucleon but 0 protons, right? Okay. And on this side, it's a 1, 1 hydrogen, right? So I just substitute what it is, and then plus 14. Why did I put a C down there? This is a 6, right? Okay, 14, 6. And so somebody's already saying nitrogen. Let's see. This has got to be, the mass number's got to be 14, doesn't it? Yeah? Because I got 14 and 1 equals 14 and 1, right? Yeah? So whatever the mass number is, it's got to be 14, and then the bottom number has got to be 6 plus 1 has got to be 7 plus 0, right? Which is, yeah, indeed, that's just regular old nitrogen, right? Where did we see that? What's the different one? Yeah. That's not so hard. Is that hard? Way easier than chemical stuff, right? Especially like, do you guys ever do redox reactions? Reduction, oxidation? Yeah, those were like the hard ones to balance. I love that though. Ta-da. Yay. Let's try that. Whiteboard, 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 whiteboard. Whiteboard, 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 whiteboard. That was your first example